Hey Frank, welcome back. Just waiting for Alex. Alex, if you're here, please let me know. All right. Here we go. Sorry for the delay today. Having some internet problems. Had to reboot my internet and try it out again. So I just unplugged it, give it a shot, and hopefully it'll be good. All right, so welcome back. Hopefully you guys are all doing well, staying safe. I'm looking for Alex. If you're here, Greg, Alex, if you're here, please let me know. Couple things. I did post something yesterday. It's all right. I hear you, Frank. No, that happens. So I did post something last night. I was scrolling through the TV last night and noticed there wasn't too much on TV, and I stumbled upon this channel 13 Spectrum. It's WCNY. It's mainly like an educational channel. Channel 13 for Spectrum. It was Nova Beyond the Elements, and it was on reactions. So the subtitle of that was Reactions, and it was pretty cool show to see on TV and to relate to, at least this class. So I had to post it last night. If you saw it probably like 20 minutes into the segment, or I posted it like 20 minutes into it just to make sure it was legit before you guys watched it. And I enjoyed it. Hopefully you had a chance to watch some of it. It did a really good job explaining different types of reactions in society. So maybe I will play portions of that throughout the duration of the year. But I know next Wednesday night, they're going to also premiere another segment of Beyond the Elements. It's Nova again, Channel 13. Next Wednesday night at 9 o'clock, it's going to be on indestructible materials. So it's going to be like different elements made up of indestructible materials. So instead of being reactions, it's going to be really synthetic stuff or man-made materials that are really tough. So feel free to check that out if you'd like to. All right, the COVID report today, I don't think too much has really changed. Yeah, I think this is the same data from yesterday, so 51 cases. So not much for me to really go through for the COVID report for today. 2,596 cases. That number has decreased over the duration of last week. 15,246 have been resolved. I'll just stick with that for today. Let's go to the classroom page for today, see what's going on today. A lot of examples on solubility curves. Here we go. Quote of the week comes from Colin Powell, and there are no secrets to success. It's a result of preparation, hard work, and learning from failures. Daily agenda for Thursday, February 4th, 2021. Today's a day one. We are continuing on with unit number 6, which is properties of solutions. We're going through topic 2B. You're finishing up 2B today. It's the third day talking about this topic. So today we're really going to analyze examples on the solubility curve. We'll go through the rest of the examples that we didn't finish up last time. Watch a portion of this YouTube video. And then I switch the order a little bit. Warm up will be towards the end of class. That'll be a chance for you to explore and analyze some questions. And then whatever time's remaining will be for you to complete the rest of the questions, the exit pass on topic number 2B, solubility curves. Anybody have any questions or anything you want to share with myself or classmates? Sun's out. Take advantage of this. Maybe after school today, go for a walk. Get some of the sun rays on. Spring's will be right around the corner. So hopefully back in school soon too. All right, so you definitely need a reference table. You need a reference table. You need the examples, which is the first thing above. And we analyzed 6, 7, 9, and 10 yesterday. So we're going to finish up the rest of these right now. So please open up this assignment. We'll finish up the rest of these questions. Hey, Alex, try to get here a few minutes early. Take out a reference table, and let's try to go through some more of these questions. So again, I'm going to put the questions that we already analyzed up here. So today's class is really driven by you guys. How quick you guys work today is how much time you're going to have for the exit pass. But the first couple I'll go through. If there's questions you haven't seen before, I'll go through it again. We already did questions number 6, 7, 9, and 10. We'll do the rest of them. Yes, I'm not grading the examples. Those are more for you guys to know how to do them, to see some examples. The exit passes are what I grade. All right, so let's check out question number 1. Here we go. Question number 1 reads, which compound decreases in solubility as temperature of the solution is increased from 10 to 50 degrees Celsius? So if I'm analyzing this question, the first thing I see is it wants to know which one's going to decrease. There's got to be a decrease. Insolubility of temperatures of the solution increases, so temp is going to increase from 10 to 50. A decrease in solubility. So what I would do here is figure out maybe your zoom annotate, or maybe you want to highlight your reference table, or maybe you made copies of this chart to highlight. I would have provided you several copies so you could mark up several of these charts, but what are you going to do? So what I would do is figure out where each of these curves are. I'm going to color code them. Find NH4Cl, NH4Cl. Let me hold up for a second. Before I do that, I'm going to look at the temperature ranges from 10 to 50. So all I care about is the temperature range from 10 to 50. So I'm going to just highlight this and not get rid of all of it. Just going to make it transparent, semi-transparent. And the only segments I care about are in that window that's not highlighted. All right, so now let's find NH4Cl. There's NH4Cl. I only care about that curve. It's not highlighted. So there's NH4Cl. Next up, find your NaCl. NaCl, oh, there it is. NaCl, boom. It's a slight increase. Next one up, we have NH3. Find NH3. Looks like it's decreasing as temperature increases. Again, that's going to be your covalent bond or gas. And the last one, locate NaNO3. Find NaNO3. That's going to be increasing with temperature increases. So again, we're looking for one that's going to decrease. Let's check them out. Let's check out the pink line again. The pink line, oh, it's increasing. So pink line is increasing. We want to decrease. Can't be that. Next up, let's find NaCl. If you zoomed in on your reference table, checked it out, there is a slight, it's a small little increase, but it's increasing. No, not the best answer. Next up is NH3. Oh, there's that yellow line there. Check out that yellow line. It's a pretty big increase. Yeah, that's decreasing. I'm sorry, decreasing. Pretty big decrease. And the last one, if you check it on out, NaNO3, the green line, from start to finish, is increasing as well. So in this situation, the only one that is decreasing is going to be that yellow line there. So everything else is increasing. The yellow line is decreasing. It's got to be the best answer. It's the best answer. Number one, best answer is C. One is C. Let's check out number 2. All right, the following data was recorded while determining the solubility of a certain salt. That tells you a lot of information. A salt is an ionic compound. Which graph best represents the solubility of this salt? We have temperature data. We have grams of solute per 100 grams of water data as well. So you could take these data points, you could look to the left and say, oh, it's a solubility curve. I have points, I have the scale I plotted there. I have my temperature I plotted. I could just plot these points as is. Or, so you could just plot these points just like how you see them. So you see 10 and 30, sorry, 10 degrees and 30, plot, 20 and 33, plot, 30 and 36. Oh, it looks like this one actually. 40 and 39. Plot, and then 50 and 42. All right, there you go. It looks like it's going to be KCl. So what I suggested before is just like to white out this curve, or all the curves, and you can figure out what that's going to look like. Obviously, you can match that up to what's to the right. what am I talking about? If you wanted to, since you have this digital world now, you could have started fresh and just plotted those points, and then you would have realized it would have been the same or similar to that curve that we just plotted. Plot, whatever. So something like that we just had there. What's this look like? It's got to be choice A. A is definitely a good choice. Everything else is decreasing. Or it doesn't look like choice D. No. It's not going to flatten out like that. So this choice number two of the best answers is going to have to be choice A. Does anybody have any questions on 1 or 2? All right, let's try number 3 out. I think I'll let you guys do this one. Yeah, try number 3 out. Take about a minute. I'll take a minute to do it, and then I'll ask for answers at the end of it. Hey, question number 2, please record your answer in the chat. Question number 2, please record in the chat. Yeah, it's once you figure out the curve, once you figure out the chart, it should be a relatively easy question. Thank you. Thanks for the responses. Like to see that. So everybody that responded put choice B for the answer. You could have figured out solubility. Hopefully it triggered in your head solubility. Where did you see solubility throughout the year? You saw it in table G, solubility curves. And there you go. Solubility of a salt, a given volume of water. Solubility per given unit of water. Best thing's going to be, it's dependent on the temperature of water. You see temperature from 0 to 100. That's the x-axis. That tells you solubility. Number 3, the best answer is going to be choice B. Number 4, please try this one out. Number 4, which compound shows the least increase in solubility from 50 to 60 degrees Celsius? Minute 30. Three, the best answer was choice B. 3 was B. You're welcome. Kyle, I'll go through that in a second. Figure out a way for you guys. Record your answer in the chat for number 4. Didn't get through all of them. Trying to field some questions there. Okay, a couple different responses I see popping through. A's and B's. Which compound is least soluble in water from 50 to 60 degrees Celsius? So least soluble in water. All right, least soluble, you're looking for the lowest solubility. So lowest solubility is going to be the lowest number. So solubility, you can see up on top, there's 150. As you go down, the solubility is going to have to decrease. So which one's going to be the lowest value here? Lowest value in the curve at this temperature range looks like it's going to be the NaCl. Least soluble, choice B, NaCl is the best answer. So B is the best answer for number 4. All right, someone asked how number 4, the best answer is B. Somebody asked, how could you draw on this chart on mine? So on my settings, I don't know, please tell me if you do. On my settings, when I look at my Zoom screen, I don't know what you see. There's a little toolbar that pops up and pops down, or maybe it stays up for you guys, depending on what you have. And on that toolbar, I have a annotate. It's like a little pencil. Do you guys have that or no? So you could draw on the screen. So if I mute, stop video or video, do you have annotate by remote control or anybody check that out for me? Do you have that setting for annotates? It's like a little pencil. Oh, sorry about that. Thank you. I did see this message. No, you don't have it. No. I'll have to see if there's a setting to change that. So it doesn't look like you have that feature. What you could do, if you want to draw on this each and every time, you could take, I have it, but I can only draw on the Zoom screen. Gotcha. All right, so that feature doesn't work out for us. So I guess maybe your diagram that you have that we put in our notes, you could take this diagram each and every time. You could double click on your drawing. And when you have a question related to that, or actually, we'll put this into a drawing. I didn't put it into a drawing before. My copy, insert drawing, new. If you put it into a drawing, this is the only thing I could think of right now, so you could edit this. If you have something called Cami, you should be able to look at it too. So if you have it into the drawing board, then you're able to mark it up as well. You guys have a hard copy. If you want to mark it up your reference table, you can. But from this drawing here, you could obviously mark up like kind of like how I'm doing it as well. You could change the colors, change the density, all that stuff, kind of like how, or similar to what I did as well. Hopefully it helps. I don't really know any other ways to really go through it. We could block out segments with shapes. Sorry. So maybe you want to do a split screen with this. You're drawing there. It's totally up to you. That's all I got for you. Sorry. I wish I had a better answer for that one. All right, question number 5. We want to know, according to reference table D, should be G, which compound solubility decreases most rapidly from 10 degrees to 70 degrees Celsius? Take a minute and a half to try that out. Okay, please record your answer in the chat if you derived an answer. Thanks, guys. All right, so a lot of B's, looking good. So let's check out B. Looks like a good answer. Choice A, I'm obviously going through the work. I'm trying to color code it in case you can't follow or figure this out on your own. I kind of just sit here quietly and just do this to save a little bit more time as well. So you can see my yellow line is indicated from 10 to 70. It is increasing. We're looking for a decrease, so that is not a good choice. Next up, the NH3 from 10 to 70. What's going on here? It's going to be decreasing. There's a pretty big decrease of that. Next up, the green represents HCl. HCl is decreasing too. The slope of that is not going to be as great as NH3. And the last one, KCl. Let's check it out. KCl looks like it's increase. So right from the get-go, there's two garbage answers that are not decreasing, A and D. So hopefully you got stuck between B and D. Hopefully you looked at the slope of each of those, or the difference of the rise over the run. If I look at NH3, looks like a difference similar to that. So you can see it goes 10, 10, 20, 30, 40, 53 maybe. Maybe it drops down to 53. So it decreases to 53. Let's check out the green line of HCl. Check this out. So you can mark up your reference table too. And it looks like it drops from 10 to 70 to this point. How big is it? How much? I don't know. Let's say it's 10, 25 maybe. So a difference of maybe 25. Quick little estimate of that. So 25 would be the drop of that one. So yeah, choice B is the best answer for number 5. 5, best answer is B. Again, seems like a lot of B's here. Moving on forward. So 5 is B. Number 6 we already did. Number 7 we did. 6, 7, 8 we didn't do. So 2 more questions. 8 and 11. Let's check out 8. All right, this one I do want to talk about. So I'm not going to give you, maybe you could try it on your own, but I'm going to go through it since it's a different conversion type of question. All right, question. What's the total amount of grams? We're looking for grams of potassium chloride. Potassium's K, chloride Cl. You could figure out the formula if you needed to. Needed to saturate, so it's got to be on the curve. Exactly 300 grams of water at 10 degrees Celsius. So like any chemistry question, I go through, I highlight the important information, I figure out what you're looking for, and then hopefully you can make that connection. It didn't say check out table G. Hopefully you can make that connection. You see saturate, you see water, potassium chloride. It's a total number of grams. Hopefully you know it's going to be table G. You're going to have to analyze. All right, so I go through my checklist. We have water, and the first thing I look at is it says 300 grams of water. So I did this last time. Put a red flag above water. Water. I want to look at the y-axis, and my water's amount of water I'm starting off with. Can't make a straight line. The amount of water that I'm starting off with over here on the y-axis is 100 grams. So there's a problem there. You're going to have to convert to get to 300 here. How do you get from 100 to 300? You just multiply by 3. So you're going to multiply that by 3. But save that for the end. But know that this is at 300 grams. You're going to have to convert this at the end. So if you need 300 grams, you multiply by 3. If you needed 200 grams, 200 Gs, and it said 100, you're going to have to multiply this by 2. And the other situation they might ask about, if they say you want 50 grams of water, to get from 100 to 50, you're going to have to divide the factors by 2. But we'll practice that for the warm-up in about a half hour, 20 minutes or so. All right, so let's go through this. We're going to figure out we'll convert at the end. So just convert at the end, make it easier for you. Got my big red flag, I won't take that away. The one variable that I have to start off is 10 degrees Celsius. So find 10 degrees Celsius. All right. We have potassium chloride. So find potassium chloride, KCl. KCl, I'm gonna mark it all up. So when you do have a question like this on the Regents, benchmark, whatever it may be, there's gonna be, well, benchmark might have a few more questions, but for the Regents, you'll have one, maybe two questions on this chart. So you'll be given a fresh reference table, a new reference table, so feel free to mark it up however you want to. There's KCl, and it says to saturate. The point of saturation is going to be on the curve. So at 10 degrees, how are we going to saturate this solution? It's going to have to be on the curve. So at 10 degrees, follow it on up. Where's the line intersect with KCl? Right where the heart is. The heart of Tafiti. Looks like it's about 30 grams. I think that's like one of the best Disney movies, Moana. My kids ask, what do you want to watch for a movie? I tell them Moana every time. Check it out if you never checked it out. So I don't know, maybe you will in the future. 30 grams of solute per 100 grams of water at 10 degrees Celsius. So this is going to make a saturated solution. If I want a saturated solution of KCl, if I have 100 grams of water, if the temperature is at 10 degrees Celsius, all I need is 30 grams of solute. But if I want it to be 300 grams, so let's take a break for a second. Let's rewind. Time for a nice little drawing. All right, so I have a picture. So what the heck's going on in chem class right now? I'm taking a beaker, I'm taking a pitcher, whatever you want to call this. Call it a beaker, like we're in chem class. Here's a beaker. And inside that beaker, I'm gonna put some water. I'm gonna put 100 milliliters of water or 100 grams of water. I don't care. So I'm gonna have 100 grams or 100 milliliters of water. And the temperature is gonna be at 10 degrees Celsius. So inside this beaker is 100 grams or 100 milliliters of water. 1 milliliter equals 1 gram. And it's cooled down to 10 degrees Celsius. So it's a really cold water. If I want this to be a saturated solution, so I want this to be a saturated solution of the compound, ionic compound of KCl, I need to add 30 grams. So let's say my stars, each star represents 10 grams. So if I put 10 grams in, I stir it. If I put 10 grams in, if I stir it, it is going to dissolve. Easy. So put 10 grams in, it dissolves. If I put 2 stars in, that's 20 grams. If I stir it, it's going to dissolve. If I put 3 stars in, 10, 20, 30 grams of KCl, we're calling this. If I put 3 stars in, if I stir it, I'm gonna stir it, stir. Some of it is going to dissolve quickly. If I keep stirring it, it's going to eventually dissolve. And if I keep stirring it, it will get to the point where it just dissolves. It may take some time, but it does dissolve. It's still a homogeneous mixture. So that was with 3 stars, 30 grams of KCl. If I put 4 stars in there, 1, 2, 3, 4, it's 40 grams. So if I'm at 40 grams, it's super saturated. I could stir this as much as I want. Some of it will dissolve, but there's still going to be a solid that is not going to dissolve. So this would be the point of super saturated. Not all particles are going to dissolve. There's a precipitate or a solid that will form or won't dissolve there. But back to this question. Talking about 30 grams I put 30 stars, 3 stars in there, and they all dissolved. If I change this to 300 milliliters of water, I have a bigger beaker now. I like these drawings. Guess I'm having fun with them. So I go from 100 to 300 milliliter beaker. Bigger beaker, bigger pitcher. Oh, messed up that line. If I put 300 grams of water in there, so if I went from 100 to 300, it's not to proportion. This is in the beaker. So my water now is 300 grams or 300 milliliters of water. The temperature is still going to be at 10 degrees Celsius. I want to know how much solute I have to add to make a saturated solution. So the picture to the left, we had to draw, we put it in here, we added, oops, darn it, messed up my colors. The picture to the left, I added some KCl. It was equal to 30 grams per 100 grams of water. If I have 300 grams of water, it's going to be similar. We're just going to take that 30 and multiply it by 2. So I think you guys, most of you guys probably understand this so far. KCl in this situation, we're going to have to multiply it by 3. 3 times 30 is 90 grams per 300 milliliters of water or grams of water. So obviously, to make this a saturated solution, it's definitely a bigger volume. You're going to add more solute to the solution. And all you have to do is multiply it by the factor. A lot of stuff for that. Any questions on the drawing? Talking about what just happened there? So 100 to 300, you multiply by 3. 30 to 90, you got to multiply by 3 too. All right, last question, number 11. Question number 11, here we go. Please try this one out. Based on reference table D, a solution of NaNO3 that contains 120 grams of solute dissolves in 100 grams of water. At 50 degrees Celsius, it's best described as what? Please try this out. Give you a minute to do it. Once you're done, please put your answer in the chat. Once you find an answer, please put the answer in the chat. It's okay, Joey. Yes, Alex. Yes, Mike, thank you. Thanks, Zen. Thanks, Nadina. Correct. Yes, Faith. Yes, Irvin. Thank you. Eight should have been 90. 8 was 90, whatever that choice was. You're welcome. All right, so here we go. Let's check out this last question here. We have 120 grams of solutes. I highlighted that in blue. We have 50 degrees Celsius. I highlighted that in green. So when these 2 points merge, I put a little heart there. That's going to be my reference point. So that's going to be the reference point. The curve we're analyzing is NaNO3. Color that in yellow. We're out of 100 grams of water. There's no conversions I have to do. And it wants to know that heart, that reference point, in terms of this curve, is it going to be saturated or supersaturated? So yeah, it is above the curve. Since it's above the curve, it is going to be supersaturated. So above the curve, supersaturated. Supersaturated, point above the curve. Saturated is a point on the curve, and below the curve is unsaturated. But anyways, it's supersaturated. All of these hearts in the situation that I'm going to draw, they're all above the curve at that given temp. All these hearts would be supersaturated. Above the curve, supersaturated. All these X's I'm going to put are on the line at the given temperature are said to be saturated or at equilibrium at that temperature. And all the stars that I'm representing here, no matter where they are, they're underneath the curve. They are said to be unsaturated. So stars are under the curve. They're going to be unsaturated. X's are on. They're saturated. And the hearts are above. They're going to be supersaturated. So this one's going to have to be supersaturated. It's definitely not saturated. It's not on the curve. It's close, but it's not on the curve. So it's not A or B. So you have a 50-50 shot getting that right now. The term supersaturated means there's a lot of solutes. Dilute means there's not much of a solute. It's watered down. Something supersaturated, there's a lot of particles in there. You can see them. It is concentrated. So your Kool-Aid has a lot of sugar, has a lot of powder. Something supersaturated, a lot of flavor to it. If something's diluted, it's watered down. Dilute always goes with unsaturated. So dilute and unsaturated go hand in hand. Saturated could refer to concentrated as well. All right, so that's it for the example questions, 1 through 11. Does anybody have any questions on anything here before we move on forward? All right, you do not have to submit this. These are example questions that we went through in class that we did together. There's no notes today, so I don't need that. Next thing up on the drawing board is going to be a flick. I'm not going to play all of it. I'm just going to play a portion of this for today's class. Enjoy.
It falls from the sky. It makes up 60% of our bodies, and just about every chemical process related to life takes place with it or in it. Dihydrogen monoxide. Without it, none of the chemical reactions that keep you alive would happen. None of the reactions that sustain any life form on Earth would happen. Not even the majority of inorganic chemical reactions that shape the surface of the Earth would happen. Water is the key to nearly everything, and one of the reasons it's the key is because it's really good at dissolving stuff. We need it so bad that we dump over 180 gallons of it into our bodies every year, and we do that in order to maintain an aqueous or water-based solution inside our cells, because aqueous environments are pretty much the best for cool chemistry. Each and every one of us uses water for all kinds of chemistry every single day. Our body chemistry, our food chemistry, and yes, our laundry chemistry all take place in water. Ugh. This used to be a white sock. It is now a little bit of gray sock, and in places a little bit of a yellow sock. But anyway, I want it to be white again, and to do that, I'm gonna need some chemistry. To whiten whites, you might use a solution of sodium hypochlorite, better known as bleach. What makes bleach so good at its job is that it's a really strong oxidizer, meaning that the oxygen atom is really good at pulling electrons away from other compounds, making them break apart. This is really handy for getting rid of stains, but as you can tell by the formula, sodium hypochlorite also contains chlorine, which happens to be really good at killing things. That's why we use it in swimming pools and as as a disinfectant. But there are lots of other good oxidizing agents, and one that doesn't contain chlorine is hydrogen peroxide, and it can be used as a bleach too, but its only components are hydrogen and oxygen, just like water. We'll talk about oxidation and other kinds of reactions in a couple weeks, but before we get to that, you have to understand solutions. And before we do that, I'm just gonna get rid of the laundry because it's kind of stinky. This bottle of hydrogen peroxide contains a solution, and not just the solution to my problem of stained laundry. By solution, I mean a solution of liquid with another substance dissolved in it. Here, water is the liquid or solvent, and hydrogen peroxide is the solute or dissolved material. And water is an amazing solvent, possibly, arguably, the best solvent on Earth. Why? A lot of reasons. There's a lot of it on the surface of the Earth. That helps. Just abundance is good. It's liquid at a very wide range of temperatures, and being liquid is what you need to be able to be a solvent. But also because it's polar. It's a very polar molecule. Remember how I said that oxygen is really good at pulling electrons toward it? Well, oxygen atoms are more electronegative than hydrogen. The oxygen atom pulls harder on the molecule's electrons than the hydrogen does. As a result, the electrons in a water molecule tend to spend most of their time near the oxygen, giving the oxygen end a partial negative charge and the hydrogens a somewhat positive charge. This polarity makes water extremely effective at dissolving things, especially other polar things. The sugar we mixed into our tea last week, for example, was polar. When you mix a polar solid like sugar into a polar liquid like water, the molecules of the water surround the sugar molecules. The negative side of the water molecule is attracted to the positive side of the sugar molecule, and vice versa. And interacting with the sugar molecules, the water inserts itself between all of the individual molecules of the sugar that were once clumped together in the sugar crystals. A liter of water can dissolve as much as 1,800 grams of sucrose. Water-based solutions. Earlier, I called them aqueous solutions, and I'm calling it an aqueous solution again so that you remember it's called an aqueous solution. Aqueous. You could create all sorts of aqueous solutions using salts or minerals, even acids. Ethanol, which composes 95% of this grain alcohol, is polar, so it dissolves easily in water. But water does not dissolve non-ionic, non-polar substances. Oil, for instance, doesn't have any polarity, so it has no interest in interacting with water. So when you mix them, they separate. Water's polarity also gives it lots of other super useful properties. For example, water can decrease the attraction between ions of different charges. We call this its dielectric property. Take table salt, for example. It's made of positively charged sodium ions and negatively charged chlorine ions. When it's mixed with water, the water dissolves the salt into its component ions. The water molecules then surround the individual ions and shield them from each other's electric charges. These ions in water are called electrolytes, literally loosened electricity, because separating them through dissolution frees them to act independently and carry their electrical charge around. You've probably heard about electrolytes in biology class, but you've definitely heard about electrolytes in Gatorade commercials. Your body needs electrolytes to carry electrical signals that help your muscles twitch and your brain cells fire and get all the business of living done. In addition to helping you live, electrolytes are one of the most important ways chemists have of classifying solutions. Pure water on its own does not conduct electricity, which seems a little weird to us, the whole hair dryer in the bathtub thing still being a terrible idea. But if you put a bit of salt or any other ionic solid in the water, they dissolve into those component electrolytes. It's the electrolytes that are conducting the electricity. It's not what you might expect, but we have Swedish physicist Svante Arrhenius to thank for figuring this out. While doing his doctoral research in the 1880s, he first developed the idea that a solution's electrical conductivity could be linked to the concentration of ions in the solution. It was one of his predecessors, British super genius Michael Faraday, who discovered that substances dissolved in water conduct electric currents. Faraday was terrible at naming stuff, though, so he wrote to a guy who was known for coining terms, William Whewell. You may have heard of his most famous creation, the word scientist. Whewell wrote back to Faraday saying, "I would propose for the two elements resulting from electrolysis the terms anion and cation, and for the two together, you might use the term ions." And there's something interesting here, and I didn't pick up on it at first, but Whewell said the things resulting from electrolysis. Faraday thought that the electric current is what produced the ions. What Arrhenius discovered was that water simply dissolves certain substances, like salts, into their constituent ions, which themselves carry the charge. And since electrolytes carry electric charge, the higher the concentration of electrolytes in a solution, the higher its electrical conductivity. Arrhenius found that you can even reverse engineer your study of a solution and by measuring its electrical conductivity, figure out how concentrated it is. Despite the importance of his work, Arrhenius's chemistry professors didn't think much of it, and he got a mediocre grade, which is why it must have been particularly sweet when he won the Nobel Prize in 1903 for that very same research. Today we know a little bit more about how electrolytes work, and we've learned that the relationships between their concentration and their conductivity is not always straightforward, because not all electrolytes dissolve equally well in water. A strong electrolyte, for example, is one that dissociates or breaks apart completely when dissolved in water and conducts electricity very well. Salts do this, so do strong acids like hydrochloric and sulfuric and nitric acid, as well as strong bases like sodium and potassium hydroxide. Weak electrolytes only dissociate partially when dissolved in water, so they're only somewhat conductive. Most of the solutes molecules stay stuck together, remaining neutral. Acetic acid, the active ingredient in vinegar, and ammonium hydroxide are examples of this. And of course, some things dissolve in water but don't conduct electricity at all because they don't dissociate into ions. Alcohol and sugar, for example, are non-electrolytes. Now, what does any of this have to do with my laundry? Well, hydrogen peroxide is a polar molecule, so it dissolves really well in water. But it's a very weak electrolyte. When it dissolves, it tends to dissociate into a water molecule and a lone oxygen ion. Since the dissolved peroxide creates even more water, the concentration of ions is quite low. But that lone oxygen ion is not happy by itself. It goes on an oxidizing rampage, swiping electrons from anything it can find. It's especially good at tearing up the tricky double bonds that tend to give laundry stains their color. When that rampaging ion destroys the double bond, the stain disappears. We're used to thinking of hydrogen peroxide as a fairly mild chemical, but that's because the over-the-counter stuff is pretty dilute. Too much peroxide could actually dissolve my clothes, and some of my favorite shirts are in here, so we need to dilute this stuff to make the solution the right strength. And as you might expect, if you joined me on my recent foray into stoichiometry, when chemists think about the strength of a solution, they think about moles. So before we can dilute this formula, first we have to figure out how many moles of solute of hydrogen peroxide we're working with here. You'll remember, I hope, that 1 mole of a compound equals 6.022 times 10 to the 23rd molecules. That is...
Okay, I'm going to cut that video there because next class we're going to talk about moles and molarity and parts per million. So we'll begin into that next time for class. The rest of the class today, let's go through and go to the warm-up today. Should say cool down or warm up. Sun's pretty hot today. So please click on the warm-up 2-4-21. It's topic 2B, solubility curves. So I'll finish up these questions and then I'll give you the rest of the time to work on the exit pass. Please click on, this is going to be more for you to do. I don't know. Do we want to do group breakout rooms or are we good not doing them? Anybody have any preference? I haven't done group breakout rooms in forever, but I feel like we have a pretty good thing going on. I feel like we're more productive. Faith, do you want to go to group breakout rooms to do these questions, or should we do them all together? Or the way we've been doing it? It's up to you, Faith. You make the call for the class today.
I like when we do them together. Oh, my phone's going off.
All right, sounds good. Thank you. All right, so please take out your reference table anyways. Breakout rooms are cool, but I don't know. I don't know how much we really get accomplished in them sometimes. Question number 1. Here we go. Which compound shows the least increase in solubility in water from 50 to 60? I'll give you a time frame. Put my time frame on my phone. Give you 2 minutes. Try it out. Okay, please put the answer in the chat once you're ready. Wait for 5 responses, and we'll move on forward. Extremely loud. Thanks, Faith. Thanks, Asim. Mike, thank you. Thanks, Nadina, Zen, Kai, Joe. Oh, a lot of responses. Thank you. B is the best answer. B, the least increase in solubility. I do like teaching actually this lesson virtually because I can actually mark this up. I put these little arrows indicate, obviously I color code it, and I could put these arrows indicate the type of increase it's going to be. If it's a small increase, if it's a big increase, you can see my choice B is the smallest arrow, the smallest increase in solubility. 1 is choice B. 1 is B. Next up, number 2, graph shown represents the 4 solubility curves. Which curve best represents the solubility of a gas in water? 1 minute. Okay, please put the answer in the chat. Looking for the gas notes, you can find the gas. Yeah, so covalent bond or the gases are going to be decreasing solubility. So my pink font over here, my notes from yesterday, covalent bonds, they're all decreasing as temp increases. The only one that's decreasing here is going to be choice B. Everything else can represent an ionic bond. So 2, the best answer is going to be choice B. Thank you for your responses. Number 3, here we go. Which saw has the greatest change in solubility from 30 to 50? 30 to 50. Let's get a minute and 30 seconds. Okay, please put the answer in the chat once you derive an answer. Wait for 5 responses. Okay, I'm having a couple different answers, a lot of A's and some C's as responses. So greatest change in solubility. So the greatest difference in solubility could be increase or decrease from 30 to 50. All right, you can see the segment I only care about is between 30 degrees and 50 degrees Celsius. I highlighted the colored curves indicate the different ionic compounds. So let's figure out the greatest change. A, KNO3, let's check it out. difference is the y interval. So how much is it? How much is the difference? I guess I'll just stick here 10 right there, 20, 30, and some change. So maybe like 33, 34. Maybe the difference is. So I'll say that's going to have a difference of 34 for solubility. Let's check out C. People said C as well, the pink one, the pink font. Let's check out the difference there. 10, maybe 20. So an estimate 10, maybe 20 grams is the difference in solubility for that one. So the greatest change is going to be the greatest number for the y-axis. Looks like KNO3 is the best answer for that one. Greatest difference, the greatest slope is going to be KNO3 within that duration from 30 to 50 degrees Celsius. Best answer there is choice A. A is the best choice for number 3. Try number 4. Give me 30 seconds on this one. Please record the answer in the chat. Number 4. Yes, Jumila. Yes, Zin. Emma, good. Alex, good. Asim, good. Urban, good. Yes, Nadina. Choice B. Yes, Faith. So equilibrium exists. Equilibrium exists at saturation. The point of saturation, that's where equilibrium is existing. Equilibrium, it's in the notes as well. The point of saturation, there's a question like this on the exit pass as well. Best answer. 4 is B. 4 is B. Next up, number 5. A solution is formed between dissolving 45 grams of NH4Cl and 100 grams of water at 70 degrees Celsius. Which statement correctly describes this solution? Let's go with a minute. Give it a shot. Please put the answer in the chat once you derive an answer. Thanks, Faith. Thanks, Asim. Zen. Thanks, Irvin. Alex looks good. Jumila looks good. Thanks, Nadina. All right, if you're playing along at home, every response that I have is correct. Choice B is the best answer. My reference point is my heart, the heart over there to the left. I have 70 degrees Celsius. I have the curve NH4Cl. So hopefully you're looking at this saying, oh, this is not that bad. There's a lot of stuff on this chart, but you analyze one at a time. If you break it up one at a time, it's not nearly as complicated as it looks. Show it to your friends. They might be discouraged, but you know how to read this now. 45 grams, we have 70 degrees Celsius. We have 100 grams of water. The reference point's the heart. And it's under. That heart is definitely underneath that yellow line, unsaturated. NH4 is a solute. What you add to the solution, what is being dissolved is the solute. The solvent is water, dissolves the solute. 5, the best answer is going to be choice B. 5 is B. Number 6, a couple more questions. Part 2 question on the reagents. There's 35 short answer responses similar to this. Student uses 200 grams of water at temperature 60 degrees Celsius to prepare a saturated solution of potassium chloride. According to table G, how many grams of KCl must be used to create a saturated solution? Let's go with 90 seconds. Okay, please record the answer in the chat for number 6 if you came up with an answer. Yes, Jumila. Yes, Al. Yes, Nin. Yes, Nadina. Yes, Irvin. I didn't get as many responses as the last one. Going through this, we have 60 degrees Celsius. I have my green line represents my KCl, and that's my reference point. The heart is my reference point for 100 grams of water. The question wants it out of 200 grams of water. So again, what I have to do here, from 100 to 200, how the heck did you get there? All you did was multiply it by 2. That reference point for 100 grams of water was equal to about 45. So I got 45 over here for a saturated solution. If I have 200 grams of water, to make that into a saturated solution, I take 45 times 2. And that would give us an answer of 90. Yeah, close. 90 is better. Good. 90 grams of solute would be added to 200 grams of water to make a saturated solution. Good. So 90 grams of water, best answer. Number 7, last one. Finish it up. What's the total mass of KNO3 that must dissolve in 50 grams of water at 60 degrees Celsius to make a saturated solution? So 50 grams of water this time. Let's go with a minute. Give it a shot. Okay, that's a minute. Please record your answer in the chat if you had a chance to go through it. Okay, a few answers. Got A and B as responses. All right, so you went through this process. I found 60 degrees Celsius. There's a dark red line. I have KNO3, it's a brown line. And we want saturated. So saturated, before I convert, we have that heart right there. That's the point of saturation. It looks like it's 105. Maybe 105 per 100 grams of water. The question's asking about 50 grams of water, so you have to convert that. How do we go from 100 grams to 50? You divide by 2. What you do there, you have to do the same thing to the solute as well. Divide it by 2. That's the answer. Looks like it's going to be choice B, 53. All right. Anybody have any questions on that warm up for today? Analyze a ton of solubility questions. All right, again, you can submit that if you want. You don't have to. The rest of the class today, I'm going to give you, I don't know, it's about 10 minutes left. Time to work on the exit pass. This is going to be graded, obviously. Exit passes, I do grade. This right here is what I'm going to grade, and you have now to the rest of the class to complete it. If you do not finish it for some reason, it is going to be assigned for homework. If you already did it, you're good to go. If you want to hang out from now to the end of class, you're more than welcome to, and I'll help you out with whatever questions you may have or guide you with those questions you have. There's 10 questions. If you pay attention today, yesterday, then you probably could handle these all by yourself. If you hang out, I'm going to ask that you join the breakout group in case you have any questions. If you want to leave, have a great day, make good decisions. Go for a walk out today. Take advantage of the weather. See you guys later. Bye. If you're going to hang out and join the breakout group. And if you have any questions, please feel free. I'll help you out. See you later. If not, bye guys.